Good day, students. Welcome to our another online session for the course Computer Organization, and this session is specifically designed for the students of BEE 7A. And till now, we've discussed about the single cycle processor, its basic functional modules or the components upon which the processor comprises of, and then we've discussed about how the instruction cycle is being processed by the single cycle processor in detail. We have also seen the combinational part of the processor and the sequential components of the processor, and we've said that this processor has the capability to execute all the instructions in one clock cycle, and the clock cycle time is basically dependent upon the slowest instruction or the combinational path, the longest combinational path in the system. That is basically the critical path of the system. So we have to set the clock cycle time according to that, and so that all the instructions can be processed in one clock cycle. Then we have also discussed about the control signals and the sequential components of the design in detail. And in today's session, we will basically gonna execute our instructions on the basic single cycle processor, and we're gonna see how the instructions are processed, or in other words, how the instruction cycle is processed by these functional units, and what are the steps through which an instruction is executed or processed. So let us start our first example with the R-type instruction. And if you remember that the R-type instructions are those instructions whose all the operands are basically the registers. So let me write an instruction for your kind reference. For example, we've got an instruction of add $S1, comma $S2, comma $S3. So if we see that in this instruction, this is basically the addition instruction, and all our operands is $S1, $S2, and $S3 are basically registers. That's why we call it as the R format instruction. And if you remember that the format of the machine code for the R format instruction was first 6 bits were opcode, then 5 bits each were for RS, RT, RD, RS, RD, and RD. Then we have got the shift amount, SHMT, 5 bits each, and then we've got 6 functional bits. Where RS, RT, and RD are the addresses of the register. For example, this is RD, this is RS, and this one is RT. So RT is pointing to $S3, RD is pointing to $S1 in the register file, and RS is pointing to $S2 in the register file. Got it? So for the first step, this instruction, let me label as static instruction, and let us assume that it has okay, let's don't assume the machine code at this stage right now. So let's be generic. So first we have fetched this instruction. Let's assume that the instruction that has been fetched is this one, static. So we've got a 32-bit machine code here at this line. Let me highlight that. So we are at this stage. Then RS, RT, and RD, if you see in the diagram here, bit number 26 till bit number 31, this is opcode. We have separated those lines and applied the opcode to the control line, to the control unit. So this is basically our opcode from the instruction. Okay, then we've got the RS, this is RS, this is RT, and this is RD. Okay, so according to the RS, RT, and RD, we've read two operands from the register file, that is RS and RT. For example, let's for the sake of discussion that we've got $sign S1 equals to 100, $sign S2 equals to 200. I am writing in hexadecimal basically, this 100H and 200H. And for example, $sign S3 that is equal to 300. Okay, so when this instruction is fetched, before execution of this instruction, we've got the content of $sign S1, $sign S2, and $sign S3 equals 100, 200, and 300. Now the addresses of these registers in the register file, $sign S1, $sign S2, and $sign S3 are provided by RS and RT and RT to the register file. And what would be the output of the register file at this specific line? Let me change the color so that you can differentiate that. At here, read data 1, we are getting the content of $sign S1. This is $sign S1. So here we are getting 100H at this line. We are getting 100 at this line, and on the second read data 2, we are getting 200. Now what would be the value of this multiplexer so that this 200 should be provided to ALU rather than the sign extended value, that is the other output, other input of this multiplexer. That is dependent by, if we see that the control signal, that is ALU SRC, if you see that control signal, let me change it. See here, this one, let me use a highlighter. This one here, this line. So this line basically decides that the second input of ALU should be read data to other than that sign extended data, that is all the second input of the multiplexer. So what the control unit do in this scenario, when control unit receives the opcode of this add instruction, control unit generate ALU SRC equals to 0. So in that scenario, we will get ALU SRC equals to 0. This thing is ensured by a control unit. When we are designing the state machine, we will ensure that whenever there is an instruction of the add or the R format instruction, this control line should be selected at or connected at 0, so that this data, read data 2, should be forwarded. This data should be forwarded to ALU rather than the data from this line extension. So ALU got the two inputs 100 and 200. The operation is add operation. What ALU will do is ALU will set this ALU OP, and we have discussed in a previous class that the table which we have discussed, that the values of ALU OP. This is 2-bit line along with functional fields. See here, these are the functional bits. These are the bits, 6 bits. ALU control will basically select the adder, and ALU result will get 200 plus 100 equals, sorry, 200 plus 300. Basically $sign S1 was the destination operand. We have the read data 1 would be the content of $sign S2, and read data 2 would be the content of $sign S3. Kindly make this correction, that here we are getting 200. Here we are getting 200 from the register file, and here we are getting 300. So the first input of ALU is 200, that are the content of $sign S2, and the second input is the content of $s3, that is basically 300. The ALU result that is produced, the result of the addition, that is basically 500H, which is basically, if you see that this line is connected to this multiplexer. So now control unit will do that. Control unit will set this select line or this control line, that is basically if you see that, that is mem to reg equals to 0. Mem to reg equals to 0, so that the data from data memory is not being provided to the register file, but data from ALU would be provided to the register file. And from here onward, the data will move at this line to the register file, and whatsoever the value of RD is, the data is written in that particular register. So in this way, the R format instructions are being processed. And if we see that the utility of the processor or the data path, we have not used the data memory, although this section is present here in our processor, but we haven't used that for the R format instruction. Similarly, this header is also not used, this portion is also not used, this portion is also not used. Okay, got it? So in this particular way, the R format instructions are processed. So after execution of this instruction, $S1 will get 500. Previously it has got 100H. Okay, so in this particular way, the R format instructions are processed. Well, that was all for this session. In this session, we focused on the implementation of the R format instructions. So in our next session, we will be discussing the processing of loads and stores basically. Till now, have a safe day, and we will see you again. And best of luck for your exams as well, which are coming in this week also.